we can see who the truly dedicated 6004 students are. Thank you. Okay, so we do have a quiz review this evening, 7:30. This one is in 34101, which is the auditorium that's on the first floor of building 34, just that way, 50 yards. So see you there if you want to come and work through some problems with JD and Olivia. After this week's quiz, we sort of will, over the weekend, switch into design project mode for people who want to work on the design project. There's, lots of lab hours this weekend. There's lab hour. We'll make sure we have lots of people in the lab next week. So if you're looking to score a few points off the design project, we'd be happy to lend you a hand. So take advantage of that. And finally, we have a favor to ask of you, which is, could you help evaluate 6004? 004 is a machine that over the years has been tuned up, and we're always looking for advice about how it could be better or different or whatever. And we also appreciate give you a chance to evaluate us. All this is very helpful. Sylvina and I will certainly read through everything that you write, so feel free to take a blank space in one of the forms there, or one of the questions, and type in any comments that you have. And the department looks at them pretty carefully too. So this is your chance to give some feedback, and we would very much appreciate it. So thank you. So today we're going to talk about how to hook things together. Typically, when you buy a CPU, there's lots of things you want to hook to it. You want to hook up memory, you want to hook up I/O devices, you want to hook it to the global network. And so we're going to spend a little bit of time thinking about some of the issues behind hooking things together, look at some technologies from the past, and look at the technologies we're using today. So it's an interesting question to ask. When we make a long list of all the technologies that we discuss in 004, which ones are sort of long-lived? What's the thing that 10 years from now you will say, oh yeah, I remember we talked about that in 004. And the thing is that technology is moving so quickly that sometimes you say, well wait, why would I bother to learn about any technology? It will be different tomorrow. So that's a good question to ask. And the answer sort of is that it turns out that a lot of the technologies themselves aren't the key asset that survives decade in, decade out. It's the interfaces between the technologies. In other words, how a disk actually stores information, and whether it's a solid-state disk or a rotating magnetic disk, that all changes, and it's changed dramatically in the 50 years that I've been sort of looking over the shoulder of computers. The thing that hasn't changed, or at least in recent years, is the interface. So for example, there's a very specific interconnect technology we use to talk to disks. And people who want to start a disk company, what you can do is if you speak SATA or something like that, you can make your fantastic new Quark disk work, start selling it tomorrow, because if you provide the right interface, people can plug it into the system they already have. Okay, so my advice to engineers, such as you, is to really put a big investment into choosing your interface, making sure that you've got the right abstraction, one that won't change the next time there's a new integrated circuit process, or the power supply voltages change, or something like that. What you want is something that once you invest in it, people can reliably use that to talk to you, even though you may be changing and improving and making bigger profit margins or whatever it is your goal is on the insides. And one of the things that we've learned is that virtualizing things is a good plan. So at the end of the day, display technologies will probably change dramatically. It may be that 5 years from now, if I'm lucky enough to still be lecturing, everybody in the audience, instead of having their laptop open, will have these big black goggles, and they'll be doing whatever their virtual reality thing is. almost certainly not involving the lecture hall, but whatever the new distraction is. But the point is that if I want to write a program that displays things to the user, I don't want to discover the actual low-level way in which LCD screens are driven. I want to use an abstraction, an array of pixels or something like that. So inventing sort of a nice abstract interface can actually make it so that people can work with whatever your devices are for years to come. There have been lots of examples of very poorly chosen standards that only last for a couple of years, and then you have to throw the whole thing away. And I'll show you some examples as we go along. There's been some interconnect technologies which certainly fall in that category. I can remember a great phrase I learned the first year I was here, 1973. Anyway, there was an engineer up in the AI lab called David Moon. He was probably one of the best software engineers I know. We were chatting about this new text editor called TICO. Text editor and corrector. TICO is sort of the forerunner of Emacs. TICO is what we used on teletypes before we got to Emacs on video screens. Anyway, he was describing why people get sort of sucked into that particularly keystroke driven editor. And he says his phrase was a moment of convenience, a lifetime of regret. There's a lot of truth in that, and there's a lot of technologies that we just throw it together. This is convenient. This is great. And then decades later, we're still going, oh my God, why did we choose to do that? If you look at the Intel instruction set, there's an awful lot of instructions. Look someday if you're really interested, look up the AAA instruction. Just AAA, x86 architecture, and you look at that, and you should ask yourself, why would anybody think that was an instruction that ought to be implemented in hardware? And the answer sort of was, well, there was a brief moment in time in which that seemed to be a significant operation. However, the next 30 years of Intel processors all have to implement the AAA instruction, and you're sort of going, oh my God, you can just see the Intel engineers wishing they could go back in a time machine and killing off a few of carefully chosen instructions so they weren't stuck with them. Okay, there have been good success stories. I think by far, to me, the best success story has been the interface standards for networking. Okay, the whole notion that the actual electrical interface to the networks have been sort of slowly improved over the years, but the packets that I drop onto the network today and to get them delivered around the world look a lot like the packets I dropped onto the network in the early 80s to get them delivered around the United States. So some of these standards have been well chosen. Some of them represent fundamental shifts. So now how many people think that 2 to the 32 is a big number? That's about 4 billion. Right, so that sort of seems like a big number. Certainly when we were designing the addressing scheme for the internet, the ARPANET, which at that point had 30 some odd nodes connected to it. We were node 18, by the way, here at MIT. And the notion of a network address space that allocated 32 bits for a packet address, was just incredible. It was like 4 billion. There's never going to be 4 billion anythings on the network, right? Now we've reached the phase where MIT has 4 billion things connected. No, not quite, but the idea is that it turns out that this 2 to the 32 number is small compared to the number of things that want to hook to the network. We're out of IPv4 addresses. We need to go to IPv6. 64 bits. How many people think 2 to the 64 is a big number? Yeah, so here we are. Remember this little conversation? So 30, 40 years from now, when you're giving this lecture, you can raise your hand and everybody will laugh, saying, oh, 2 to the 64, how stupid could we have been? So anyway, the point I'm trying to make is there's some choices that seem like they're a lifetime and sometimes they're not. So it's fun to think about which one those are and think a little bit carefully. You know, maybe having an encoding scheme where you can change the size of the number you're representing would actually be the best way to do packet addresses. So you could make it work for 32, but it could, you know, that same mechanism could be expanded to 64 or 128. You know, that's the sort of flexibility that after you've been around that tree 2 or 3 times, you say, next time it's going to be expandable. None of this fixed stuff. Okay, so back to interconnect. So, you know, when computers first came out, there was only a small selection of boxes. These are all big boxes. Each one of these things represented a rack panel. And there was specialized cables that ran between them. And whatever the engineers felt like, you know, what do I need to do to talk to the tape drive? Well, put those signals, bundle them into a bundle of wires and you know, have a plug at either end, and we're ready to go. And that sort of got extended into, instead of a whole series of ad hoc connections. So in the original computers, you'd look back and there would be this big connector labeled connection to memory 1, and then there'd be something labeled connection to memory 2, and connection to memory 3. And if you happened to have a memory 4, you'd look in the back and you'd go, dang, you know, there is no connector labeled memory 4. And so people got sort of interested in a more sort of general purpose, you know, interconnect that works for everything. And all of these processors here were these signals on this sort of expandable backplane bus were peculiar to a particular processor. So, you know, cards that you plugged into an IBM backplane were not the same as you plugged into a Digital Equipment Corporation backplane. In fact, if you had suggested the idea, everybody would have just laughed at you. Okay, until we got to the era of the microprocessors, in which the notion of having a bus, which might represent a technological standard that survived, you know, that lasted for longer than any particular interface, you know, signaling specification, it seemed like a good idea. And in fact, from an, you know, it was great. The only thing that, the real reason that buses have sort of disappeared is that making something that is this long run at a gigahertz clock rate turns out to be hard, because it turns out light only travels this far in a nanosecond, right? And so we weren't able to get the information across the width of a 19-inch rack panel in the 1 nanosecond cycle time that we had, because light wouldn't travel that distance, right? And so this notion, this neat, fairly, you know, it was a fairly clean sort of architectural idea of building these processor-independent interconnect buses, okay, failed simply because of speed. Okay, nowadays, this picture here is sort of reminiscent of, you know, where things got to, because the processor to memory interface needed to be, you know, much higher speed, much higher capacity than the processor to you know, network interface or to the disk. And so recognizing that we needed different speeds, ultimately what we did is to generate a bunch of different buses, each of whom was still fairly general purpose, but designed for a particular trade-off in terms of bandwidth and the length of the bus. And nowadays, people have sort of given up on the notion of these general purpose buses. Everything is just a piece of specialized point-to-point communication. You can buy, you know, from integrated circuit manufacturers, when you put together your cute integrated circuit to do something, you can drop in high-performance bit serial communication links like PCIe. And we'll talk a little bit about that. Okay, so let's talk a little bit about sending information on wires. Okay, and it turns out that as a theorist, wires seem very attractive. You just think of them as an equipotential node. And there was no notion that something would be different on a wire. You talk about putting a signal on the wire, and at least in the abstract, distance and time are sort of not there. The notion is that was just telling you that this information is shared everywhere in the circuit. And you've been drawing lots of wires in your JADE schematics. And the idea is that any signal that is put onto that wire sort of, you know, arrives more or less instantaneously at the destination. The reality, unfortunately, turns out that's not a very good abstraction. Because even over very modest distances at the speeds that we're talking about today, it turns out the distances matter, how fast you're changing the signal matters, the actual medium of transmission. I mean, everything, it turns out all these details that we abstracted away by this notion of this ideal interconnect pretty much come back to bite us as soon as we try to do anything other than to get a signal from one NAND gate to the next NAND gate. That distance, the sort of, the handful of microns distance is still, you can treat wires as wires. But as soon as wires get to be a millimeter long and certainly a centimeter long, then they turn out to be fairly complicated electrical devices where time and space matters. So here's the abstraction that we like to deal with. We can sort of think of moving information in time and space, and if we move information in time, we think of that as storage. In other words, I put it in Tuesday, come back Wednesday, it's still there. We would say that we've moved information across time, so we characterize that as storage. Whoops, how about going the other way, Chris? Whoops. And the communication is moving information across space from me to you. The truth of the matter is, when we actually look at real physics, that any sort of communication involves a little bit of moving across space, but also moving through time. Information takes a while to get from me to you. And the speed of light from me to the back row is represents 50, 100 instruction times on a monoprocessor, right? I mean, this is a vast distance. This room is large, very large, compared to how long it takes to us to execute an instruction in the modern world. Okay. And so you say, well, let's put everything close together. Well, of course we can't. There's just not enough physical room to put too many high-performance processors in a 1-foot cube. There's a limit to how many of those we can do. So we're very much faced with the physical reality these days. Okay, so the real truth about wires is thinking them as sort of abstraction, and we have a delay that we use that sort of represents both the intrinsic delay of the gate and also the time it takes to get where that signal is going. That's the timing model we use in 004. The reality check is that if I have too many gates hooked to a signal, it's slow. And in fact, you'll meet this in the design project. And Jade actually uses a more sophisticated timing model, which has partly an intrinsic delay in the gate, but also as you take a signal and it goes to many, many, many places, that signal will get slower and slower and slower. As you increase the number of, it's called fan-outs, as you increase the number of fan-outs, the number of devices that you connect to send information to, the slower your signal is. So all of these things matter. So, what happens is that you design a neat architecture, you quick draw up a logic schematic, and then you spend months and months and months worrying about how to build this thing so it can actually run at a reasonable speed. And you spend a lot of time thinking about, is this signal does it have to go too far? Is it too heavily loaded? How do I address all these problems? Okay. So, the initial scheme, back when wires were short compared to the times that we're talking, the system times. So back when things ran at 10 megahertz, right? Okay, which is 100 nanoseconds. Something that's this long, that's only a nanosecond or so. So you have 100 nanoseconds to get information through your system, a 32-bit word or something from one place to another. That was long compared to the distances involved. And so we built these backplane buses, which were just long pieces of copper wire with connectors on them, and the connectors let you plug in boards that could basically make electrical connections between signals on the boards and signals on the backplane. And that was a pretty neat technology and worked really well for the first 50 years of electronics. And long about 1990 or in the late 80s, it turned out buses started to have lots of issues simply because of the speeds. The buses tended to have many wires because they represented all the things you needed for a transaction between a producer and a consumer. Okay, so here's how it might look. Typically there was a clock on the bus that would tell everybody when to look at the signal. So at the rising edge of the clock, people who were putting signals onto the bus would put them on. And at the falling edge of the clock, everybody would say, okay, when I see the falling edge of the clock, I'll look at the bus and look at the wires to see what I'm being asked to do. So there's a notion of a master. Who the master was might change. And so the master would start off by first signaling, hey, I'm starting a cycle. So there's a start signal. Then he'd put on an operation, maybe a read or a write operation. Maybe if you're addressing memory, everything, or you turn everything into a big piece of address space. And so the notion of what you wanted it done was encoded in the operation. The notion of who you wanted to do it was encoded in the address. And the notion of what it was, the piece of data, was encoded on the data wires. And so the master typically would certainly set up the operation and the address, and on reads, whoever out there was going to be respond, the memory card, would send back the data. On the writes, of course, the master would supply the data. And at some point, after some number of cycles, the slave would say, aha, I'm done, here's your answer. So there's very sort of, so the slave could take so the master initiates transactions and slaves perform them. And so, the slaves could take multiple cycles if you asked for something complicated. So this worked pretty well. The whole issue of carefully separating when you put a signal along and when you looked at it took care of a lot of issues of clock skew, so that not everybody sees the same clock edge. So if we all did everything on the rising edge, it may be that you started to, if I'm the master, I will have started to change my signal before the rising edge reaches you, some number of nanoseconds later, and you're still trying to look at the last signal on the bus, right? So this notion of separating when you look and when you change the signal was sort of important to make these protocols work in the 100 megahertz timescale. Then the bus had some responsibilities. Its job was to keep track of requests that were being satisfied by nobody, and to be sort of the default slave that would basically assert some sort of response code and say, I'm done, and there was usually an error code it put on the bus saying, and nobody answered, so this is your nobody was here signal. Electrically, putting information onto these backplanes was complicated, particularly when you started putting the signal on in the middle of this big, so you have a card in the middle that's trying to communicate to cards at the end. Signals would basically reflect off the end of the buses. As soon as you take some EE courses, if that's in your future, you'll discover that at every impedance discontinuity, a little bit of energy gets reflected. Right, and so certainly having a wire, a 50 ohm wire that just stops, if you put a signal down it, you discover all that energy that's busily been making its way down the wire will actually reflect off that infinite impedance at the end, this impedance discontinuity at the end, and you'll get an echo. Right, we're used to, you can hear the echo in here. We're used to echoes. That's something that we expect. If I put energy that way, it bounces. It doesn't get absorbed by the wall. It just bounces back. And so, as it turns out, echoes from previous transmissions can complicate the reception of the current transmission. So it can actually get quite confusing. And a lot of communications engineering is spent dealing with so-called intersymbol interference, the notion that your transmission medium has a delayed response, an impulse response that causes some of the energy, some of the information from previous transmissions to basically corrupt the current one. Okay, so the notion that we had to wait for the echoes to die down started to say, well, first of all, why are we getting echoes? And secondly, that's going to limit the speed, because if I had to speak each word so that the echo was gone by the time I started the next one, okay, the lecture would be even more tedious and slow than it already is. Okay. Alrighty. So that was sort of the state of things, people sort of willy-nilly just putting signals on these perfect wires and then wondering why they seemed slightly less than perfect, but maybe if we pretended it was okay, it would be okay. Meanwhile, we started thinking about communication through whole buildings, the so-called local area networks. And then, of course, some places in the 60s and 70s started worrying about communication across the US, so the dawn of the networking age. And so Bob Metcalf, whose office was 3 doors down from mine in Tech Square, started working on inventing the Ethernet. And so this was the idea was that this neat guy in Hawaii had done this radio network to transmit data between the islands, between the different pieces of the University of Hawaii. And well, we couldn't set up an entire satellite downstation. It didn't make much sense anyway to have a satellite downstation going from floor 5 to floor 9 in Tech Square. So instead, we put the ether, we captured it in a coax cable, and that was sort of our broadcast medium. And everybody was basically playing little radio transmitter, and we basically send these little packetized communication, okay, through the network. And the architecture was pretty neat, though. So the notion of a packet, the notion of a packet with a checksum, so you could see if it has been corrupted at all. The notion of telling whether somebody else was transmitting by listening to the medium or noticing that your packet got corrupted during transmission was enough to say, okay, how do we do sharing? And the reason, we sort of do it by everybody sort of listens, and if it turns out there was too much talking at the same time, different people would back off and say, well, I'll wait and I'll send my packet a little later, thank you. And so there was this exponential back-off scheme. It was actually all cleverly engineered to solve a bunch of problems so that basically a bunch of independent, autonomous things, simply by listening to what was happening on the ether, could arrange to share a communication mechanism. And of course, people have been doing that in radio for a long time, but now we were talking about much tighter timescales, much greater information transfer happening. So this was the start of actually being sort of serious about engineering communication. Certainly the Ethernet very quickly discovered that they needed to terminate their wires in order to get rid of all those echo problems. Real engineering was going on as part of the networking effort. And not only in the hardware, also in the software. Because as it turns out, there were competing low-level technologies for sending bits on the wire. There was the Ethernet, there was something called the chaos net, which was, so the Ethernet was something that Bob Metcalf worked on, a bunch of people up in the AI lab on the 9th floor of Tech Square. I keep saying Tech Square, so back then it was 545 Tech Square, now it's 200 Tech Square. I mean, why they renamed it, I don't know, but they did. Anyway, so the AI lab was on the 9th floor, and I was in lab for computer science on the 4th and 5th floors. And the idea was that we had a different net, they had a different net called Chaos. IBM, who was on the 2nd floor, the IBM Cambridge Research Lab, was on the 2nd floor, and they had this thing called Token Ring. Everybody had a different idea about how to get information on and off wires efficiently, and they were optimized for cost or performance or what have you, or maybe in the case of IBM, profit margin. But quickly we began to realize to intercommunicate we needed to be a little bit more sophisticated. So this notion that we would have a physical layer which involved how bits were actually encoded on the wire, okay, and how packets were transmitted and received. At a higher level, we had this notion now of a network layer whose job it was, here's an abstract packet, right, which had an address and a payload and a checksum, and if everybody was capable of looking at the address and saying, aha, okay, that needs to go to California, thank you, and independently of the actual physical network, we could get information around. Okay, so this was the Internet protocol, and then above that was TCP. So anybody know what TCP is? Transport Control Protocol? So IP and TCP used to be one protocol, but they were split, right? So IP is in charge of simply getting a packet somewhere, delivered somewhere. TCP is what most of us use to actually build a communications channel that delivers the packets in order, okay, and takes care of packet losses and things like that. So if you use a TCP connection, you basically get a reliable stream of bytes. Across what at this level is a best efforts network. Packets can disappear. It's up to TCP to figure out what packets disappeared and ask for them to be retransmitted and all that stuff. Anyway, this layered communication protocol is the thing I mentioned earlier as being quite successful, surviving many generations of technological changes at this end. Okay, it's allowed us to build new types of transport protocols. So there's real-time protocols. The UDP is sort of like a datagram, which doesn't involve some of the guarantees and overheads of TCP. IP has really connected the world, and we're all the beneficiaries of that. So it was a long-lived piece of technology. Kudos to Dave Clark and Dave Reed and all the other Daves who made it work. Okay, so what are some lessons we as engineers might learn from the networking world? One is termination. The notion that energy, if you put energy and you start moving energy around, you got to do something with it. You just can't simply let it get to the end and bounce off and create echoes and stuff like that. So if we have in this case, this is a differential pair. We're basically putting a positive signal on one wire and a negative signal on the other. A way to think about this is we're measuring the difference between the two wires to get the signal. That's what differential signaling is all about. Look at the difference between the two wires, which turns out to be very reliable to certain types of common mode noise. Maybe that makes sense. Maybe it doesn't really matter. The notion, though, is that if you simply try to if you put a signal and you make some you change the relative voltage of those wires, if you don't terminate it at all at the end, you get these awful echoes, right? So this is a signal that's supposed to look a lot like that, okay, but ends up looking like that unterminated. If, however, you put the correct termination is a very fancy word for a resistor. Okay, that sits here. You can get active termination. You can get more complicated termination, but for most of what we do, this a simple resistor termination. And the idea is to sort of put a resistance here that makes it look like the wire goes on forever. So if you think about what the effective resistance of this wire, if it was infinitely long, and you simply put that resistance here, okay, the signal gets there and says, "Oh, I'm not stopped at all. I still have forever to go." So I no energy reflection. Right? And the signals clean up dramatically. You dissipate a little power. And electrical engineers sort of go, yeah, I know that. But this whole notion of doing termination well came as a surprise to those of us who were in computer science who said, what's this hard thing about hardware? Well, we learned that hardware had some interesting mysteries, and one of them was termination. So termination, pretty much every signal these days is terminated, and that causes us to be able to get reliable communication at factors of 10 and 100 and 1,000 greater speeds. So the best thing you can do, the gold standard is differential signaling, and the reason is that if a lightning bolt happens, like that. There was a great article in the Times about somebody who's famous for making nature sounds just with their voice. I don't think I should have brought him in today, and he could do the lightning bolt for us. But the notion is that most of the things that would change the voltages of these wires would actually end up changing the voltage on both wires the same amount. So differentially, if you're looking at the difference between the two wires, even severe electrical disturbances have no net effect. And so you can say, well, it looks like there could be a loop here. Maybe I'm capturing magnetic field. So these are usually twisted pairs. In other words, the two wires are twisted together in such, just mechanically twisted to make a braid that it basically is pretty impervious to almost all sorts of electrical interference. In controlled environments, often what's called single-ended signaling will work, and that's just because doing these differential pairs is sort of a bit of a pain from laying out your PC board point of view. The worst thing you can do is to have a single wire that's shared among multiple drivers. There's all these issues, electrical issues with impedance problems and the fact that depending on who's transmitting, people receive slightly different waveforms. This is not a good idea in the modern era. So another thing that we learned is if I'm going to send you information, I'm going to wiggle a wire up and down and tell you that I'm sending you ones and zeros. Do I also have to send you a clock signal that tells you when to look at the wire? Do I have to say, look, at the rising edge of the clock, look at the wire. If it's high, it's a 1. If it's low. And so now you say, wait, does that mean I have to send everybody 2 wires? That seems sort of awkward. And the answer is no. There's a very clever scheme. Suppose you saw this waveform on a wire. These are digital samples, so that's why they're dots. And you look at this and you say, wait. If on the rising edge of the clock the signal changes, I can actually infer where some of the clock edges were. Because, at least relative to me, as I'm looking at the waveform that I'm receiving, I can say, well, there must have been, if the transmitter had transmitted the clock to me, I would have seen rising clock edges right when the signal changes. So whenever the signal changes, I can say, that represents, the notion of a clock edge. And then using the clock frequency, I can infer all the other clock edges. and then I can carefully sample sort of reliably in the middle of each of the transmitted cells. So the notion of clock recovery based on transitions of the signal is how pretty much everything works. What happens if I send all zeros? Oops. There's no edges, right? I mean, the wire's always low. And so what happens, we actually use a clever encoding scheme, the most famous of which is so-called the 8B10B encoding, which was invented by IBM. And the notion is I take 8 bits of actual data, and it could be all zeros, and I encode it into this 10-bit piece of information that's guaranteed to have a couple signal transitions. And so in an 8B10B encoding, you go at most 6 clock periods before you're guaranteed to have a transition edge. So these automated clock recovery that's looking at transitions to recover when, the sampling clock at the receiver has enough edges to work with. Right, so that's, so this notion of recoding, you can, a lot of problems that you can, in communication, you can often solve by a clever recoding. You can deal with error detection and correction. There are lots of things you can do with recoding. So in this case, clock recovery. Alrighty, so where are we in our story? We started off with the Ethernet up over there in Tech Square. Everybody really bought into this point-to-point thing. People began to realize that was the gold standard for reliable communication. So now everything we own is 10 base T, or 100 base T, or 1,000 base T, or 10,000 base T, or, and what that means is that we basically, it's all point-to-point, and the T, we have both transmit and receive wires. So when you plug in a hardware network connection, you're plugging in a wire where information comes to you over, and if you want to send information, you send it on a different wire. And so there's these 2 wires. And so the number just tells you the sort of bandwidth of the signaling that's happening. Okay, and then what happens is to actually get everybody hooked up, we have basically all these hierarchy of switches. So everywhere you look at MIT, there's these closets that are full of different levels of switch. Right? There's switches for this end of the floor, there's switches for the whole floor, there's switches for this building, there's switches for a group of buildings, there's switches for all of MIT. So these are sort of hierarchy of point-to-point communications. And if I want to send something from here to Tang, it travels through a whole set of switches. And in fact, if you run traceroute, you can actually see the switches that you go through. Okay. All right, so now everything is point-to-point communications, whether the distance is small, that's between me and the memory. So your DDR DRAM has a very carefully engineered little serial protocol that it's using to send all these little bits. Of course, it's sending a lot of these little serial protocols in parallel. Almost all communication nowadays is this point-to-point. Works really well. Alrighty, so point-to-point communication, one transmitter. There's never, if there's never a notion of, wait, now you have to send to me, so I have to get off the air, and then you can start transmitting, and how long do you wait before you start transmitting? All those problems are solved if I can always yell in my send signal and always listen to my receive signal without any notion of having a protocol about, wait, should I be listening or sending? So that's very great. All packetized, all covered by checksum, so I can tell when a packet has failed. All using a clock recovery scheme, so I can just send you the data and you can reliably extract the bits in the packet without any other information than that single received waveform. If I need many of them, I know we're going to put many of those things in parallel. So PCIe times 2, times 4, times 8, times 16. Right, you buy a high-end graphics card, right? It's a PCIe times 8 or something. And what that means is that the communication between the CPU and the graphics card is over 8 independent multi-gigabit per second serial channels. And you say, wait, I have a big piece of information and it's going to go over 8 different channels and get reassembled into a big piece of information at the other end? That sounds a little complicated. What happens if they don't arrive? All these little individual packets have to be first created at the transmitter and then received and then reassembled into the big data stream at the other end. Yes, so millions of FETs get spent doing the logic that makes these high-speed PCI, the so-called SerDes, or PCIe serialized, deserialized communication systems work. Moore's law saved our bacon. Right? We have the millions of transistors to spend. So a modern computer actually has these very high performance things. So there's a special communication bus, the DDR communication buses that we talk direct. So if you have the high-end processors have three memory channels. The low-end processors have 2, so you have to either plug in 2 sticks or 3 sticks. There's basically point-to-point communication between the processor and the memory. A very high-speed 6.4 gigatransfers per second goes off to the so-called the first hub here, and that's where the PCI Express comes in. And then a slower communications channel hooks to all the, quote, slow devices, the gigabit Ethernet, things that are slow compared to PCIe. Okay, so these hierarchical point-to-point switching systems are, that's what you own in your computer, that's what we own for communication in the building, that's what the US owns for communication across the US, so forth and so on. You get the picture. Okay, and so the sort of notion that here's one bus where everything comes and goes from, and then it's sort of spread out through all the lesser beings in our fantastical universe here of who are getting their little sliver of bandwidth to do whatever they want with. It's very elegantly engineered, and it turns out to be quite effective at delivering very high performance to a small number of customers, and basically low and medium performance to almost an infinite variety of I/O devices. Just some details about PCIe. I won't go into a lot of the engineering here, but just to notice that it also has a layered protocol that involves sort of getting information on and off the wire, a separate thing that worries about this is, if you will, the IP layer, the idea of getting the packets arriving in order and reassembling them at the far end. And then finally, this is the actual information between clients in the CPU and clients in the graphics card are looking at these things and saying, oh, you're trying to put this control information into the graphics pipeline. Fine. Well, let's spend just a minute thinking about, if I have a lot of things to hook together, how should we do it? Well, we've already talked about the bus. Architecturally, it's attractive and simple. It seems to give you, it's always cost one communication between anything and between one thing and another. Everybody can communicate directly with everybody else. The trouble is that as the bus gets longer, everything gets slower. So only in theory is the cost one. In practice, the cost sort of grows as n, or the latency of the communication grows as n. Rings are very attractive because it's all point-to-point communication, and it's very easy to expand. You just unplug the ring and stick somebody else in it, and away you go. It has a slightly longer communication latency. On the average, it's order n as you sort of go around the network. The complete graph is sort of the ideal solution. It works fine until n gets a little large. It works fine when n is 5 or 10. It works less well when n is 400 million. But the notion that everybody can communicate with anybody over a specialized link. Typically, the highest level of your communication network has these sort of things. So if you actually look at the telecommunication network in the US, you can find this complete graph at the various highest level of the data switches, right? Where there's these huge bandwidth cables that basically connect people. And so by the time I'm communicating with Google in California, my data isn't visiting lots of little places between here and California. It goes up, and then there's probably a massive fiber that's connecting some East Coast hub, probably in Boston, all the way out to some place in the valley in one big step. And so we take advantage of these things to get very high bandwidth, low latency communication at sort of the highest level of the network. Crossbars are a favorite. They sort of give the notion of a complete graph, although the actual costs tend to be a little lower. But often, if we have, for instance, 4 cores in a single chip, there's often a crossbar where the processors are talking to the memories, and it looks something like that. So crossbars are popular. Most modern, when we get 64, 128 cores on a die, typically we've given up on lots of connectivity. We have a much more regular mesh. So You can go upstairs and join a research group that's talking about on-chip communication networks, and they're looking at all sorts of exotic meshes. Maybe those will be 3D in the years to come as we get into 3D integrated circuits. Think of this as it's a fairly sophisticated network. There's actually a substantial amount of transistors devoted to receiving a packet for your neighbor, deciding whether it's for you or whether it needs to be routed. If so, which of your outgoing wires it should go on. So this is like a real little communication network that's busily taking a packet and forwarding it to the next person. So, the cost to get through this network are basically orders square root of n, where n is the number of nodes in the network. So it takes you about square root of n steps to get from any one node to any other. And that seems to be where we're going to get Knight's Landing, which is the new Intel chip that has, I forget how many, 72 processors, sort of an odd number. So that'll be something that maybe we'll all have fun experimenting with in the next year or two. They have basically these mesh networks. The notion of hypercubes or logarithmic networks, so these basically, we're going from latencies that are the square root or the cube root of n to things that are the log of n. And for large enough n, that's a non-trivial difference. The so-called fat trees, logarithmic networks, were an invention that was part of the connection machine, which was a machine that was designed by people from AI Lab here, 65,000 processors. And that was 30 years ago, right? I mean, this was a pretty innovative architecture for its time. Charles Lyserson did the network design. And so what would happen is that it would only take you logarithmic time to get from any one processor to any other. And they put much more bandwidth in the upper levels of the tree than the lower levels of the tree. So it was a clever trade-off of where do we put the energy and the transistors. And the notion was, well, we'd try to make it so that heavily loaded links would get more oomph. All right. So here's sort of a summary of sort of costs and latencies for the different types of different architectures of interconnect. And these are things theorists love to look at. As an engineer, though, we should have a slightly different view, because in the real world, we can't get, if you, even with a fancy logarithmic tree, okay, those links, some of those links are much longer than others of those links because we're forced to pack things into 3 space, given the world that we live in. And so all these theoretical latencies are actually much different when you account for, the fact that we live in a 3D reality. And so a lot of these things that seem sort of theoretically attractive turn out, as a practical matter, as you make your network bigger, they just get slower. So in the abstract, a complete graph doesn't have that problem. By the time you think about how much space it takes to pack all these different nodes together into a small cube or something, you discover that your cost, if you double this number of processors, okay, you probably have doubled the communication latencies. So, okay, so this actually turns out to be sort of a big deal. Okay, so we've gone a long way to sort of getting to these point-to-point communication networks. We have the transistor budget to actually do a wonderful job on those. That's sort of a solved problem now. Okay, now what we're more interested in is we have a lot of communication to do. What's the right architecture for connecting us all together so that you can talk to you and I can talk to the person in the back, okay, and not interfere with each other? And that's sort of people are thinking about that, particularly in terms of many cores on a die. That would be a pretty interesting area to be getting into. Okay, so that's sort of the current challenge, is the sort of the communications architectures and how to get information to flow inside of these massive chips. And given that 5 years from now we're likely to have hundreds of cores in an integrated circuit, you sort of go, okay, well, if that's going to be the case, how should we cook them up? Pretty interesting for a computer science point of view. Okay, so I'll leave you with that thought. How should 100 or 1,000 cores communicate? Maybe I'll ask the question on the quiz, and you can just give me, in 1 sentence or less, and then I'll pick a good answer, and we'll start a company together. So, alrighty, see you Thursday, our last lecture. Good luck on studying for the quiz and the design project.